Okay, we're going to talk about sound power today. And we're going to use this example of a couple speakers as our sound source. And for this example, let's imagine that they are emitting a sort of constant tone that doesn't change much with respect to time. So let's say we find these speakers and we want to know how loud they are. Well, if you're familiar with sound pressure and measuring sound pressure levels and reporting them in decibels, you might think, okay, well, I can just take a half-inch pressure microphone and place it near the object and record how loud it is and report that sound pressure in decibels. But there are some things to keep in mind with sound pressure, such as if I measure the microphone right here next to the speakers, am I going to get the same answer as if I measure back here? No. As I get closer to the source, of course, we expect the sound pressure levels to go up. Things will appear louder to us as well as to the microphone. And as we get further away, that sound pressure level will decrease. Okay? So we see in this example that sound pressure, in this case I'm going to write that as L sub P. L for being level, P for pressure. We see that sound pressure is a function of distance, right? We measure something further away, it's not measured as loud as if we were up close. Okay, so let's say we have another choice to make. Let's say these two microphones are equally distant from the sound source. They're, let's say, 1 meter away in this case, but one's sort of in front of the speakers and one's sort of behind the speakers. Will we measure the same value here? No. Speakers are pretty directional devices. They're designed to broadcast noise in one direction. And so this guy over here I would expect to be louder because it's in front of the speakers than this guy over here that's behind the speakers. And so we see sound pressure is also a function of location. Okay? So while I can use sound pressure to say how loud this device is, I also have to keep track of exactly where I'm measuring and how far away I'm measuring from that object. So that can make it very difficult to compare measurements across different facilities or measurements made by different people, because you have to specify all of these things precisely. And the truth of the matter is not everyone has access to the same acoustic environment or laboratory conditions perhaps, and so we have to be able to make these how loud is this object sort of test campaigns without so much reliance on knowing exact distance and location. And that is the purpose of something called sound power, which we're going to talk about today. Sound power is a method of quantifying how loud this sound source is without respect for how far away or where the measurements were taken. So this answer should be the same regardless of how far away the measurements were made or whether the microphones were in front, behind, and that sort of thing. So how does this work and how do we accomplish this? Well, let's start by looking at the equation for sound power, and this is sort of a simplified form. But again, I'm going to use this L for level, and in this case the subscript W means power in watts. We measure electrical power in watts. We do the same thing for sound power. It's measured in watts. So this tells me L sub W is sound power. Now this is sort of a simplified equation already, but I'm only going to look at a part of it for right now. So if we look at this first term, we see that this is a summation from 1 to n of a sort of energetic average, and then we're dividing by the number of microphones in order to get an average pressure. So these are sound pressures at all of these locations from 1 to n. In this case, let's say there are 12 microphones. We're going to sum up 12 microphone sound pressures, and then we're going to divide it by the number of microphones and then take a logarithm. Okay? So we're averaging a bunch of sound pressure measurements. Okay? So why would we be doing that? Well, this is typical for a sound power measurement using sound pressure. In this case, this gray box constitutes my noise source, and I'm going to create a surface that envelops the entire object, and these red dots here in this diagram are all representing microphone locations, okay? And so you can see I have microphones all the way around the object, and any sound that emits from this object I'm going to capture because that sound has to pass through this hemisphere that I've built over my object. If I look at a real test setup, this is an actual sound power test. In this case, it's on a computer printer. But you can see this hemisphere that goes all the way around the object as well as over on top, and these are all my microphones. And they're all pointing directly at my noise object or sound source, and they're all the same distance away in this hemispheric condition. Okay, so when we're summing these up, all these microphones, we're summing them up and then sort of averaging them all out. This is giving us the ability to sort of take the sound pressure measurement on average for the whole object without regard for the location of the measurement. If the microphone's up top, on the left or the right, we are going to average all that out, and so we get a loudness or a sound pressure without respect for the location. Now, if we go back to this sound power equation I was showing you before, and we look at this other term, we have this S and S0. So for this example, or to talk about this is going to help us. So this term takes care of the location dependence for sound pressure, right? Averaging out all the different locations, we're going to get an overall average sound pressure. This is going to take into account the distance of our measurement and correct for this, okay? So this is really, again, just a logarithm of the surface area. S here stands for surface area. So our actual surface area of our hemisphere divided by some reference surface area. This is typically 1 meter squared. So if we look at this, we build a hemisphere around our speakers. We could be measuring our microphones at this radius, right? And we'll have microphones all the way around this hemisphere. In this case, we would expect the sound pressure to be, let's say, 100, just for nice, easy numbers. 100 decibels of sound pressure measured at this distance. Now, I could also measure the same hemisphere using the same sound source using a much larger hemisphere. In this case, I'm measuring a lot further away from the object, right? So my sound pressure average, and I should really put average down here and over here. This is going to be less than our 100 decibels average pressure, right? Because we're measuring further away in this case. So let's say this is 60 dB. Again, just choosing some random nice round numbers for comparison. But we know that sound power is supposed to give us the same answer, right? So we've got two different measurement distances, two obviously different average pressures. So what we see this equation doing for us, the sound pressure equation, or sound power equation, is these terms are going to sort of counteract each other. And when one goes up, the other is going to go down to compensate for higher pressures measured up closer, so the surface area gets lower. Or if the measurement hemisphere is bigger, our surface area is going to be bigger, and so correspondingly our average pressure is going to drop, right? So as this sphere goes from small to big, this measured pressure goes down, or this term here drops. But then if we take our surface area, take the surface area of this hemisphere and the surface area of this hemisphere, do logarithms of both of those, this term is going to go up, right? We have smaller pressures and bigger surface area. Smaller pressures, bigger surface area. And the reverse is obviously true as well. So this is how we take into account the different distances of our measurement. And this is the location difference. Okay? So sound power is a function of both of these being corrected for in real time based on our measurement geometry and the envelope around which we place our microphones. Now the end result of a test like this will be something like this, where you have a sound power spectrum, in this case in the 1/3 octave band, and we're reporting a level at different frequency regions or frequency bands. For an overall value, we would sum these up or take an RMS of all of these values and we'd get some overall sound power value, and that would either meet our criteria or not. But then we know the sound power level of this object that we started with, and it doesn't matter anymore where we place our microphones, as long as we're following the standard, or how far away they are. This sound power equation here is going to take care of all those things for us, and we're going to get the same answer, even if we use drastically different test setups like we see here. Now, the sound power equation does have some more complications in it that we'll talk about in the next part, but this is just a nice basis for getting to understand how sound power can help you.